In this video, we're going to do example 5.1.2, where we're going to compare to an answer that we got in a previous example, 5.1.1, where we used a Riemann sum to estimate the volume under the surface f of x is equal to xy squared on the rectangle 1, 7 times minus 4, 4. We're now going to find the exact value of this double integral by using Fubini's theorem. And we're going to check that both orders of integration give the same answer. So let's first remember that in example 5.1.1, we found that the volume was approximately 960 cubic units. And so that is an approximation for the double integral over this rectangle R of x y squared dA. So we're going to calculate now using Fubini's theorem. Fubini's theorem we saw in the last video told us that we could calculate this as an iterated integral in either order of integration. So we're going to see what iterated integrals really look like and what how they're evaluated. So let's go in the first order of integration, and I'm going to take the x range on my outside integral. So that integral is going to be dx, and the inside integral is going to be from minus 4 to 4 dy. So notice that the inside is dy and the outside is dx. Now the function is x y squared, and so we are going to evaluate this as an iterated integral, which means we're going to do the first integral, and we're going to pretend that x is a constant and integrate with respect to y. So if we take this integral, we're looking for an antiderivative of y squared. Well, that is going to be 1/3 y cubed. So we're going to have x times 1/3 y cubed, and that, using the fundamental theorem of calculus for functions of a single variable, that has to be evaluated from minus 4 to 4. So that's the inside, right? That's this part here. That leaves the answer to this is going to be evaluated in the integral from minus 1 to 7 dx. So we'll recopy that outside integral, minus 1 to 7, and then we'll do FTC here, which means we'll plug in the 4, and the minus 4 will subtract, but we're plugging them into the y. The x is a constant as far as this integral is concerned. And so we'll pull out the constant 1/3 x, and we'll do 4 cubed minus 4 cubed, and then we have our dx. So this is going to leave, again, the integral from 1 to 7 of 1/3 x. 4 cubed is 64, minus minus, so plus another 64 dx, which is going to be the integral from 1 to 7 of 128 over 3 x dx. And now we're back to a single integral of a single variable. So we can continue to integrate just like we would for a single variable in integral calculus. So we're going to take an antiderivative here, which is going to be 1/2 x squared. We have our constant 128 over 3, and we have to evaluate this from 1 to 7, which means if we simplify here a little bit, 128 divided by 2 is 64 over 3 times 2. Oh no, I divided by that 2 already, so times 7 squared, 49 minus 1 squared, or 64 over 3 times 48, which is giving us 1024. So first of all, as a comparison, the estimate that we got before wasn't great, but in that example we had only used sort of 12 sub-rectangles, so that's maybe not as bad as it could be. And here we have a value for the exact volume under the surface of xy squared over this rectangle R. Now we've done one order of integration. We went dy dx. Fubini's theorem tells us that we should be able to do the other order of integration and get the same answer. And in fact, we're asked to check that that's really the case. So let's do the other order and make sure that we do get the same answer. So the double integral over r of x y squared dA should also be the integral now from minus 4 to 4 of the integral from 1 to 7 of x y squared. And notice if I've switched the integrals, I have to switch the dx and the dy. So here I'm going to get dx dy. Now the inner integral is with respect to x. So I'm going to take an antiderivative with respect to x, which is going to be 1/2 x squared. Y squared is just a constant. This will be evaluated from 1 to 7. So on the outside, I still have the integral from minus 4 to 4 dy. FTC part 2, so integral from minus 4 to 4. My constant now is the y and the 1/2, obviously, so I'll leave those outside. 1/2 y squared times, and then I'm plugging the 7 and the 1 into x squared, so 7 squared is 49 minus 1 squared dy is equal to the integral from minus 4 to 4. 49 minus 1 is 48, divided by 2 is 24. 24 y squared dy. We're back to a single integral of a single variable. FTC part 2 again, so we need an antiderivative of y squared, 1/3 y cubed. We'll multiply that by 24 and evaluate from minus 4 to 4. 24 divided by divided by 3 is 8, times here 4 cubed minus 4 cubed, which is going to give me 8 times 64 plus 64, 8 times 128, which gives me the same value of 1024. Same. So Fubini's theorem is very useful. It is over a rectangle, but you can switch the order of integration, doesn't matter which one, and you will get the same order as long as your function is continuous over that rectangle. In later section, we're going to see what happens when your area of integration is not a rectangle, but luckily there's a solution for that case too.